the distance between skew lines. So consider two lines, say L1 and L2, with direction vectors V1 and V2. Okay, now suppose they are skew, so that means that V1 is not a multiple of V2, and also the lines don't intercept with each other. Now imagine taking any point on one of the lines and joining it to a point on the other line, like this. Then if you do that for every pair of points on both the lines, then there's going to be exactly one line that is shorter than the rest of them. And in our diagram, that's this line here, which joins the point C to the point D. Notice also that this line is going to be perpendicular to both the lines L1 and L2, which means that this line is parallel to the normal vector n, and clearly our normal vector n is, well, we can get a normal vector n by simply calculating V1 crossed with V2. Anyway, the length of the line from D to C, which I've written as D here, this is the distance between the lines L1 and L2. And the question is, if we don't know D and C, how on earth do we calculate this distance? One way you could go about finding the distance between the skew lines L1 and L2 is to find the unique pair of planes pi1 and pi2 such that pi1 contains L1 and pi2 contains L2. So the lines are inside their respective planes. And also pi1 and pi2 are parallel. Then clearly the distance between the lines L1 and L2 is just the distance between the planes. So if you take a normal vector, and since the planes are parallel, they have to have, well, any vector that's a normal vector of one is also a normal vector of the other. So if you just project, so if you multiply the normal vector n by k, and then just keep projecting it down until it intercepts the planes at 2 points. You can do this from the origin or wherever, it doesn't really matter. Suppose we do it from the origin up here. And then you get 2 points, A and B, on the planes, and then you just calculate the distance between A and B. And that will be the same as the distance between the two planes. But, I mean, you could do it that way, but it's a decent amount of work, and there's actually a faster way to do it that we'll take a look at shortly. By the way, if we are given lines L1 and L2 that are skew, how do we know that the planes pi1 and pi2, which meet these required conditions of being parallel and containing the two lines, how do we know those two planes pi1 and pi2 are unique? Well, the answer is all about that normal vector, and since they have to have the same normal vector, because they're parallel to one another, and this normal vector has to be orthogonal to the direction vectors of the two lines. So the normal vector has to be some multiple of v1 cross v2. So that means both the planes pi1 and pi2 have the same set of normal vectors, and then also to get pi1 and pi2, given the normal vector for pi1, you just find any point along the lines L1 and L2, and that will give you the exact planes pi1 and pi2, since you already have their set of normal vectors. Alright, so how would you actually go about practically calculating this? So let's go ahead and suppose that the line L1 has equation R is equal to B1, B2, B3, so that is the OB vector, plus T times, let's call this vector V, so V1, V2, V3, and then let's suppose that L2 has equation R is equal to A1, A2, A3, so that's the vector OA, plus T times, let's use a different letter, let's say S times, and then let's call this vector u. So u1, u2, u3. Now, using the fact that the vector from C to D is perpendicular to both lines, so it's a multiple of the cross product of u and v, we can actually calculate the points C and D. Before we do that, by the way, the line CD is called the common perpendicular of the lines. So it is a line that intercepts both of the lines, and it is perpendicular to both of them. It would have a vector equation r is equal to OC plus lambda times CD. If you're asked to find the common perpendicular of two skew lines in an exam, you need it in this form. It's not good enough just to find a normal vector that's orthogonal to both of the direction vectors of the lines. You actually need the full vector equation of the line. Alright, anyway, how do we actually do this? So let's say that the normal vector n is equal to n1, n2, n3, and we can calculate it simply by u crossed with v. Alright, so let's start out with the point C. Since the point C is on line L2, we know that C has coordinates, we know that the vector OC has coordinates A1, A2, A3, plus C, where C is a scalar here, times U1, U2, U3. And similarly, we know that since the point D is on the line L1, we know that the vector OD is the same as B1, B2, B3 plus D times V1, V2, V3, where V1, V2, V3 is the direction vector of that line. To be clear, this D and this D are not the same. In fact, let me delete that D there. But that's not the only way we can calculate OD. We also know that OD is actually equal to OC plus CD. And we know that CD is some multiple of the normal vector. CD is equal to K times N1, N2, N3. And so writing this out completely, we have that OD, which is B1, B2, B3, plus D times V1, V2, V3 is equal to OC, which is A1, A2, A3, plus C times U1, U2, U3, plus CD, which is K times N1, N2, N3. Now we're assuming that we know the equations of these two skew lines here, L1 and L2. And hence we also know this normal vector N1, N2, N3, because we can just take the cross product of the direction vectors of the two lines. So that means that the only things we don't know are the letters D, C, and K, which represent scalars. And hence this whole thing just boils down to a linear system of equations. We have three equations and three unknowns. We can write this in a different way if we subtract this one from both sides and subtract this one from both sides. On this side here we get B1 minus A1, B2 minus A2, and B3 minus A3. And then on the other side, that's equal to U1, U2, U3, N1, N2, N3, and then negative v1, negative v2, negative v3 times the vector ckd. And hence you can quickly get the answer from your calculator from this point, because your calculator is set up to solve systems of 3 linear equations with 3 unknowns. Or you can use matrix techniques, or you can even just solve it as 3 linear equations. Doesn't really matter. The point is everything here is a number that we know except for c, k, and d, which you can call x, y, and z if you prefer. So yeah, this is how I would suggest solving these problems. It tends to be much faster than finding 2 planes.